In the previous lectures, we have been studying about the basics of operating systems, and we have seen about computer system organization and computer system architecture. Now, as we have the idea about computer system organization and architecture, we are now ready to talk about operating system structure. So in this lecture, we'll be studying about operating system structure, and we'll be mainly talking about multi-programming and multitasking. So operating systems, they vary greatly in their makeup internally. So we have different kind of operating systems that we know, like Windows, won't do, and so on. This operating systems, they vary in their makeup internally. Internally, the way they are made may be so much different, but they also have so many common things in them. So we'll be seeing about the common things that every operating system must be capable of doing in this lecture. So we'll be talking about the commonalities. So the first two things that every operating system must be capable of doing are multi-programming and time-sharing, or multitasking. So these are two very important topics we should be seeing in this lecture. So first let's talk about multi-programming, and then we will see about multitasking, which is also known as time-sharing. So coming to multi-programming, from the name itself, we must have understood that multi-programming means the capability of running multiple programs by the CPU. Now, a single user cannot, in general, keep either the CPU or the I/O devices busy at all times. Now, if you are not having multi-programming, what will happen is that a single user will always keep the CPU or the I/O devices busy at all the times. That is because when a single user wants to execute a particular task, he will use the CPU. So until and unless the task is completed, no other users can use the CPU or the I/O devices, because it is not capable of multi-programming. But in multi-programming, what will happen is that it increases the CPU utilization by organizing the jobs, which are cores and data, so that the CPU always has one to execute. So that means that in multi-programming, what we are trying to do is we are trying to increase our CPU utilization, because the CPU is capable of executing multiple programs. So let's see how this works. So in this diagram, we have the job, pull, and memory layout of the multi-programming system. So first of all, let us understand what is a job. So job is something that has to be executed, which may contain codes and data. So here we have a job pool, which consists of all the jobs that enter the system. So all the jobs that has to be executed, they are kept in a job pool like this. And then here we have the memory layout of a multi-programming system. So on top we have the operating systems, and these are the jobs that are loaded into the memory. So we cannot load all the jobs in the job pool into the memory, because we don't have unlimited memory, or memory's limited. So by memory, I mean the main memory or your RAM. So here in this example, we are having 512 megabytes of RAM over here. So you're not able to load all of this into the main memory. So a subset of these jobs, or some of these jobs, are loaded into the memory. So for this example, we have loaded job 1, 2, 3, and 4 into the memory. Now this operating system has to help in executing jobs by assigning the CPU to this particular jobs. So if we don't have this multi-programming, what will happen is that job 1, let's say, starts executing and is using the CPU. Now until and unless job 1 finishes its execution completely, the other jobs cannot use the CPU. So that said, that job 1 was using the CPU, and then it has to use some other resources in the course of this execution. That said, I/O devices. Now when job 1 goes to use the I/O devices, the CPU is not used, and the CPU just stays idle without being used by any other jobs. But that is a very inefficient way. So in multi-programming, what happens is that, let's say the same example again, job 1 starts executing and is using the CPU, and on the course of its execution, job 1 tries to use the I/O devices. So when it goes for using the I/O devices or any other resources, the CPU is released by job 1, and then that CPU, instead of remaining idle, it can be used by another job, let's say job 2. So job 2 can use the CPU until job 1 finishes its other I/O device operation and wants the CPU back. So job 2 will be using the CPU. And again, if let's say job 2 wants to go for using some other resources and does not need the CPU at a particular time, then the CPU again, instead of remaining idle, can be used by job 3, and so on. So in this thing, we see that The CPU does not remain idle. Whenever a particular job does not want to use a CPU, the CPU can be utilized by another job. So this is a very efficient system, or an efficient way of executing. So that is what multi-programming is mainly about. So we see that for operating system to be efficient, it should be capable of this multi-programming. So we can also relate this programming with our day-to-day life. So let's say that, for example, there is a lawyer who has different clients under him. Now the lawyer is not taking care of only a single client at a particular time. Let's say that he is taking care of one client, and when that client's case is waiting to go on a trial, or when the lawyer is waiting for his paperwork to be done, he does not simply keep waiting for that single client, but at that same time, he can take care of another client that is under him. So in that way, he is utilizing his time and resources efficiently. So that is what we do in multi-programming. We are trying to utilize our CPU efficiently. Now a multi-program systems provides environment in which the various system resources like CPU memory and peripheral devices are used effectively, but they do not provide for user interaction with the computer system. So in multi-programming system, it makes sure that all our resources are used effectively, but they do not provide for user interaction with the computer system. So that brings us to the next topic, which is multitasking or time-sharing systems. So now let's see what is this time-sharing or multitasking system, and let us see how it is different from the multi-programming system. So first of all, the CPU executes multiple jobs by switching among them. Now this is almost like the multi-programming system. This first point, it says that the CPU executes multiple jobs. We have multiple jobs, as we saw above. And then instead of executing only a single job at a time, what the CPU does is it switches between the jobs, and then the switching occurs so frequently that the user can interact with each program while it is running. Now when switching happens, it happens so quickly that the user can interact with the program while it is running. So this was something that was known there in the multi-programming. So here the user can actually interact with the program even while it is running, because the switching between the jobs takes place very fast in this time-sharing system. And then this time-sharing requires an interactive for hands-on computer system, which provides direct communication between the user and the system. So this was something that was not there in the multi-programming system. There was a last point that we discussed, but in this time-sharing system there is a direct communication between the user and the system. And in this time-sharing system, as the name suggests, a time-shared operating system allows many users to share the computer simultaneously. So that computer system is shared among many users simultaneously in this time-sharing system. So let's see how this works. So in order to elaborate this point, let us take an example. They say that we have a time-shared system over here, and there are 4 users sharing this system. User 1 to 3 and 4. They are sharing this time-shared system. Now that in this time-sharing system, the switching between the jobs of the users takes place so quickly that the users themselves do not even realize that they are sharing the system. They feel that the entire system belongs to just that one person. So user 1 hittings that the entire system belongs to me, and user 2, 3, 4, they all think the same, because switching between the jobs takes place so quickly that they don't even realize that there is a time sharing or multitasking happening in the system. Now let's say that user 1, he is using this time shared system, and there is a certain job that he wants to execute. So the job is being executed by the time shared system, and then the execution of the job, it takes place in CPU speed, and we know that CPU speed is very high. So the execution of the job takes place in CPU speed. And let's say that after execution, the user has to be shown some output, and then the user has to give some input again to the system. So after the execution of the job, the output is shown to this user, and user 1 wants to give some other input to the system. That means he's interacting with the system now. The interaction between the user and the system. It takes place in user speed or people speed. That means it is taking place in human speed. So we know that CPU speed is so much higher as compared to human speed. So when he gives an input to the system, he is giving in the normal human speed. So that time gap itself is so big for the system that we have, because systems are very fast. So while he is giving that input to the system in that time gap, the CPU can be used by user for executing the job from user to so. In that way, we see that there is a time gap between the user and the system, because users are usually slower than the system. So in that time gap, the switching of the jobs takes place so quickly, and it is so quick and so frequent that the user does not even realize that they are using a timeshare system. They just feel like the entire system belongs to themselves. So in this timeshare system, it uses CPU scheduling and multi-programming to provide each user with a small portion of the timeshare computer. So, as I told you, a small portion of the timeshared system is provided to each of the user. But the user thinks that the entire system belongs to him. And how this time will be shared among the users, that will be decided using CPU scheduling algorithm, which we will discuss in detail the coming lectures. So this is very important topic, CPU scheduling, which we'll be discussing later on. And then each user has at least one separate program in memory. So all of these users, they at least have one of the programs waiting in memory to be executed. And then a program loaded into memory and executing is called a process. Now, as I told you, each of these users, they are having programs stored in memory which are waiting to be executed. And when a particular program is loaded into the memory, and when it is executing, that program is known as a process. Now this very is a important term as far as a subject operating system is concerned, process. So keep this word in mind, and we'll be discussing this later and in more detail in the coming lectures. So for now, this is all we will be discussing about multi-programming and multitasking or time-shared systems. So I hope this was clear to you. Thank you for watching, and see you in the next one.